already covered 3.2, right? Existence and uniqueness theorem. Yeah. So today we will cover 3.3, maximum interval of existence. But before that, I will ask you, let's just have a quick review on the existence and uniqueness theorem.
That would be great, because that's what pretty.
Yeah, we assume the hypothesis of that theorem still hold, so then you have to know what they are. Yeah. So here's the theorem, just a review. Existence and uniqueness theorem. So actually in that theorem we have a system, right? System. I will just write system first. I want to ask you what that is. So in that theorem we talked about solution, right? Whether there exists a solution and whether there is a unique solution for that system. My quick question is, what is the x? The x, like the dimension. What is the dimension for x in this notation? Because we want to be familiar with notation.
It has a time dimension, right?
This on this side.
Okay.
Yes, it's like a n-dimensional vector, right? X. Yes, it's a vector of n dimensions. And also each component is a function of t, right? Of t. And this right-hand side is called a vector field. Vector field, what's the dimension of this one? X. It depends on n-dimensional vector and plus the time, right? Depends on the n plus 1 variables. But this itself, capital X, is what?
It's a time-dependent vector field, so it should also be.
It's the same dimension, right?
Oh.
Same dimension. If that's n dimension, this is still n dimension, right?
Oh.
Correct? But although it depends on n plus 1 variables.
Okay.
Correct? Yeah. So this is still n-dimensional vector. But of course each component is a function of n plus 1 variables. Yeah, so quick review about the notation. So we know this vector field, right? If you pick any point, so later we can look at this. It's an initial condition, right? Initial condition at this t. What is c? Same, they should be of the same dimension, right? So this is a vector. Yeah, vector, although we use one letter, but it's a vector. So for that system, we look at the assumption, right? What's required for this to have a unique solution? So the requirement, suppose x is this one, capital X. That's the vector field. That's where it's defined, right? Where this one is defined. Where it's defined, it depends on the t and x, right? The variable. So this b is a time-dependent vector. It is from this to this, right? So a result of this, after you evaluate, this will be an n-dimensional vector. This one is a time-dependent vector field. Okay, on this B, which is a subset of R cross this Rn. What are the more assumptions? So this is one, we have a vector field, which is a time-dependent vector field. It's one thing. another thing is the partials, right? Because this one, you see, this one will map to the Rn, so we have n components, right, for this, capital X, n components. So let's suppose for each component, you can do partial derivative. These two x's are the different x's. This is a capital X. For each component of capital X, because each component depends on what? N plus 1 variables, right? You can differentiate with respect to each x variable. So you can differentiate. So all the partial are continuous. Yeah, so they exist and also continuous. That's the one assumption. Assume all the partials exist and continuous. On B, because the vector field is defined on B, which is related to time and x variables. Okay, so that's a very important assumption, because in the proof you used those assumptions to show the existence of this system. So then for this system, that means if we consider this system for every, for each point, T0 and C. So that's the initial condition, right? Initial data. For each is this. Okay, in the set B, then there exists a curve, which is called alpha, which is going to satisfy the system of equations. So there exists a curve alpha. Satisfying initial value problem. Okay, if this is the initial value problem, denoted by star. Yeah, of course this alpha maps the interval, right? Because the alpha is the solution x. This vector from interval to Rn. So this curve, there exists a curve alpha from some interval I to Rn that will satisfy the initial value problem. And so that shows the existence under the conditions, right? Under the assumption. Also, uniqueness. What if there is another curve, let's call it gamma. What if there's another curve from interval J to Rn? Of course, this interval will cover this point, right? Yeah, so if there's another curve, we can also show that curve will agree with this curve, right? So there's only one curve.
We showed that last, but that was probably the final thing we did.
Yeah, okay, so that's a quick review. So if gamma from some interval to Rn is another curve, satisfying the same in the system. Then alpha is same as gamma on that for some interval. So if we put t for any t in this interval,
What
what is that interval? Interval is the intersection of J and I.
Right.
Yeah, so on that interval, Q, which is yeah, so why do we do this? Because in the next section, we assume this condition, right, implicitly hold. So we don't, even though we don't mention it all the time, but that is the assumption also. Yeah, so that means with that condition, then it's guaranteed. We have an interval on such an interval, right? On such an interval, which is the neighborhood of this initial point. Yeah, on such an interval, there is one and only one solution. Okay, so next section is the maximum interval of existence. So the theorem, because this theorem just assumes this has the same assumptions. So maximum interval of existence. Okay, so this, we suppose X, which is the vector field here. So from B, which is a set, right? A set, a subset of R cross Rn. So the vector field is a time-dependent vector field. Okay, so X is a time-dependent vector field. Satisfying all the hypotheses of existence and uniqueness theory. Satisfying the assumptions of existence and uniqueness theorem. Yeah, so the purpose of this theorem is a little bit different. In the previous theorem, we are more interested in whether there is a solution, right? If the solution, if there is one, maybe there is another one, whether we have only one solution. So we answered that question in this theorem. But next theorem, we want to see how, whether we can find the largest possible interval so that there is a unique solution. Yeah, so this the purpose of this theorem is to identify a largest possible interval. So that's why it's called the maximum interval of existence. So we have the same assumption. That means we can go all the way here, right, to this conclusion. But once you have that, so can we make this Q as large as possible so that we still have a solution?